Suppose you have a chemical chain, and right at the end, there's a pesky carbon atom holding everything up. You want to get rid of it, to literally pluck it out of the molecule, while keeping the rest of the structure intact. In the world of organic chemistry, this isn't just a wish, it's a classic transformation known as the Hoffmann degradation. Let's look at our starting player, the primary amide. You can see it here with its carbonyl group, that carbon double bonded to an oxygen, sitting right between a nitrogen and the rest of the carbon chain, which we'll label as R. Our goal is to delete that central carbon and snap the nitrogen directly onto the R group, creating a primary amine. But notice the problem is held by strong covalent bonds. It won't just leave quietly. To kick it out, we're going to need a bit of chemical persuasion in the form of bromine and sodium hydroxide. The process begins with a bit of a tug-of-war. Watch what happens when the hydroxide ions from our base approach the amide. They're hungry for protons, and they snatch a hydrogen away from the nitrogen. This leaves the nitrogen with a negative charge, making it nucleophilic. It's now looking for something positive to attack. Enter the bromine molecule. As you can see, the electron-rich nitrogen lunges at the bromine, displacing one atom and taking the other for itself. We now have an N-bromoamide. But we're just getting started. Another hydroxide ion steps in, steals the second hydrogen from the nitrogen, and suddenly the molecule is under immense electronic strain. This leads us to the heart of the reaction, the molecular rearrangement. Picture the R group, that entire hydrocarbon chain. It sees the nitrogen is in an unstable state and realizes it has an opportunity. In one fluid motion, the R group physically detaches from the carbonyl carbon and leaps over to the nitrogen. As this happens, the bromine atom is shoved off the molecule entirely. Let's pause and look at this intermediate. This is an isocyanate. It's a strange, linear arrangement where the carbon is double bonded to both an oxygen and a nitrogen. But we're in a watery, basic solution, and isocyanates can't survive long here. Water molecules jump into the mix, attacking the carbon. After a quick shuffle of protons and the release of a stable carbon dioxide molecule, usually in the form of a carbonate ion, we are left with our final product. The nitrogen is now directly bonded to the R group. The chain is exactly one carbon shorter than when we started. We haven't just changed the functional group, we've shortened the skeleton of the molecule itself. This is the aha moment of the Hoffmann degradation. It's not just a substitution, it's a structural downsizing. It's the ultimate chemical undo button for when a carbon chain has grown one link too long. So the next time you see an amide and think it's stuck with that carbonyl carbon forever, remember that with a little bromine and base, you can simply make that carbon disappear.